Not every differential equation can be solved by hand. In this lesson, we are going to learn Euler's method, which is a numerical technique used to approximate the behavior of a solution to a given differential equation with an initial condition over a piece of its domain. So imagine that we have a differential equation which we can write in the form dy dx equals f of x and y. So this is a first order differential equation where I've put the derivative of the function with respect to the independent variable x on the left and then moved everything else to the right. We're going to name that right-hand side f of x and y because we'll use it when we write down the formula for Euler's method. This is an algorithm that you iterate as you move across the domain. So you start at some initial condition and you step with discrete steps until you get to the right side of the domain. You try to capture the behavior y that would solve this differential equation with that initial condition. So we'll look at the algorithm. We will basically derive the formula that we use with Euler's method. Then we will practice this with one specific example. So we will take a first order differential equation of this form, and from x equals 0 to x equals 1, we will generate some xy pairings that we can use to try to give an idea of how this function behaves. Since we can actually solve the equation that we'll be looking at by hand, what I can then do is put up a picture of the real solution together with the estimate that we create so that we can compare the two. So how good is our approximation? There will be a discrepancy, so it's not a perfect approximation. That will lead us to just end this lesson with a little summary of when your estimate might be an overestimate or an underestimate. Here's the derivation for Euler's method. We would like to approximate a solution to the differential equation dy dx equals f of x and y with some initial condition. You must have a point to jump off of. So we'll say, for the sake of the illustration, that at some x value x naught, y has the value y naught. In order to work through this method, let's put up a picture of that initial condition. So here's the point x naught, y naught in the xy plane. And let me imagine that this is the solution. So here we have y as a function of x that we are going to say solves this differential equation. Now, we probably don't know that if we're using Euler's method, but this is going to help us figure out what the computation needs to be. Okay, so here's what we do is we imagine kind of building up what the shape of this graph looks like by taking little steps along the x-axis. So we choose some step size delta x and step to the right with that step size. We'll call the next point on the x-axis x sub 1, and it's going to be x naught plus the size of our step, which typically will keep constant through the whole process. So every time we step to the right, we'll take a step of size delta x. Okay, I would like to estimate the value of y at this new input x1. Now, I don't have the real function here that we're looking at to plug into, but what I can do is write down an equation for the tangent line, the line tangent to the graph of this function through the initial condition x naught, y naught. So here's a picture of that tangent line. And why do we care so much about tangent lines in calculus? Because they give us a way to approximate functions with lines. Functions can be hard to work with, but lines are much easier to work with. So instead of somehow knowing the value of our function at our new input x1, let's compute the value of here I'm going to highlight it on the tangent line, the y value on the line at x equals x1. Okay, so basically, let's step a little bit to the right and find that point on this tangent line that we're looking at. For this, I'm going to use point slope form to write down my tangent line. That's a little less common than slope intercept form, so let me remind you what it looks like. We're going to say the variable y minus a known y value, which for us will be the known starting value, equals the slope of this tangent line, let's just call that m for right now, times x minus the known x value. Okay, so in general, this is the equation of a line passing through the point x naught, y naught with slope m. Okay, so that's point slope form. Let me rearrange this a little bit. I'm going to bring this to the right-hand side and say, let me just write it one more time and then we'll start actually using it on this tangent line. So y is the known y value plus the slope times x minus the known x value. Okay, this is going to look more like the equation that we're about to use. Okay, I need to specify here what the slope is for this tangent line. The way that I've written this line, we actually already have the initial condition kind of set up as the known point. So let me now find this new y value. We're going to call this y1. It pairs up with x1. So thus, y1 is equal to the starting value of y plus the slope. Oops, just dropped my marker. The slope here, which I called m, just using kind of general line notation. The slope of this tangent line is the value of f of f at the known point x naught, y naught, because dy dx is the slope of the tangent line through that point. So instead of writing m, let me write the value of the function at that point. That's the slope. Times, oh, let's make another change, and I'll use pink for this one. Here we have x minus x naught, but actually that's what we're calling this step size delta x. Okay, so in order to get from our starting initial condition point to the next point that we want to plot to start to try to build up a picture of the solution to this differential equation, we are going to say that the next y value is the starting y value plus the slope of that tangent line, which is the same thing as evaluating this right-hand side at the starting point, times delta x. That steps us to the point x1, y1. Now we just want to repeat this process, essentially like we're starting over, but with the new initial point called x1, y1. So from this point that we've just graphed, let's actually put a new solution. How about here's the solution to this differential equation which passes through that point. Now we want to step along this tangent line. The tangent line that we're looking at now has a slope, which is the right-hand side of this equation evaluated at x1 and y1. So if I want to step one more time to the right, just for the sake of this illustration, let's do one more step. We will land on a new x coordinate, which we'll call x sub 2. To compute or to estimate the value of our solution to our differential equation when x equals x2, we are going to find the y value for this point on the tangent line. The equations that we write down are going to be exactly like what we just did, but with the indices changed because we're on the next step. So let's step to the right. This time, our new x value is going to be called x sub 2. It's the previous one plus the step size. And then the corresponding y value, which we're now looking at on this tangent line, is going to be y2 equals the previous one. So here y2 equals y1 plus the slope of this tangent line. That's the value of the right-hand side, f at x1, y1. So it's f evaluated at the previous point, then once again times the step size. What would it be if we wanted to take one more step? Well, okay, here's the graph of the solution passing through this point, x2, y2. So the new tangent line is the one we're looking at. The slope of this tangent line is f at x2, y2. If I wanted to step to the right again, I would say x3 is x2 plus the step size. So y3 is y2 plus the value of the right-hand side at the previous point times delta x. So you can see that we're just going to iterate this procedure every time we take a step to the right. You keep doing this until you've either taken the number of steps that you wanted to take, or more typically, you've landed on some x value that you're interested in. Maybe you're trying to go from x equals 0 to x equals 1 with a step size of a quarter. Then you would take 4 steps to go from 0 to 0.25 to 0.5, 0.75, and then 1. So that's how many times you iterate this procedure. And each time you do it, you follow this idea that the next x value is the previous one plus the step size, and the next y value is the previous one plus the right-hand side of your differential equation evaluated at the previous point times the step size. Okay, I'm going to now summarize these steps and we will look at a specific example. Let's summarize the process now for Euler's method, and we will use this differential equation dx dy equals x plus y as our illustrative example. So this differential equation that we will work through in a minute is one that we can solve by hand, but we will work through Euler's method in order to try to estimate the value of the solution when x equals 1 and to generate a picture of the solution. So here's the thought process that I follow whenever I'm trying to use Euler's method to better understand a differential equation. The first thing we need to do is identify what our jumping off point is. That's usually given to you in the form of an initial condition. So here we're told that y of 0 equals 1. That means that our initial x value is 0 and our initial y value is 1. Those numbers will go into the computation of the next xy pairing. The next step I put up here is to compute the step size delta x if needed, really. So here we're actually told that delta x is 0.2. So you might not need to compute this, but an alternative presentation of this information could say, go from x equals 0 to x equals 1 with 5 steps. And there you need to figure out what the step size is. So let me mention that in general, the step size is, let's see, what subscript should I use? How about capital N to mean the number of steps total? So I will say x sub capital N, that's the final x value that we would compute, minus the initial one divided by the number of steps. So here, I'm trying not to overuse the letter little n, so capital N is the number of steps. Okay, so you could be told delta x right away, like we were in this example, or you could be given the starting point, the ending point, the number of steps. You have to be given enough to work out the computations that you need. One thing I'll point out is that in this problem, we would have to realize how many steps to take, or we'd have to be paying attention as we do the computation to know when to stop. Okay, so let's now go through this. So the rest of the steps here basically do Euler's method. The most time would be spent here. So step to the right, step to the right, step to the right, and then just realize when you've done enough, because you don't want to overstep and keep going beyond the final x value in order to capture the behavior of the function, or rather an estimate to the behavior of the solution to this differential equation over a snapshot of the domain. Okay, so I'm going to erase all this, and then we will go through the computation to generate the steps that we need for this differential equation. Okay, let's do the computations now for this example. You probably want to have pencil, paper, and maybe a good calculator too. The first few steps I think I can do without a calculator, but I've written everything down on paper here just in case, because while x plus y is not too bad of a right-hand side, I'm not sure I'm going to work this out all the way across the entire domain. Okay, so we started at the point 0, 1, and then we went a step with a step size of 0.2. So the x values that we're going to generate for all of the points that we use to estimate the behavior of our solution are 0.2, 0.4, 0.6, 0.8, and 1. So the x values are easy. For the y values, what we want to use is that formula. So we'll say that the next y value is the previous y value. Let me write it down as the formula the first time. So it's the previous y value plus the value of the right-hand side. Actually, let me write, I'll write f of x naught y naught. I was thinking, should I write down the actual right-hand side here? But let me leave it in general form. So it's the right-hand side at the previous point times the step size. Okay, for this particular example, our previous y value was the y value of the initial condition. Our right-hand side is x plus y. So that's going to be 0 plus 1, the previous x plus the previous y, times the step size, which is 0.2. Okay, so we've got 1 plus 0.2. So far, I don't need a calculator. Our first y estimate is 1.2. This value goes right here. So the next y coordinate, y sub 2, is the previous one. Let me write this one more time. So y1 plus, this time I'm going to write x1 plus y1. That's the explicit right-hand side times 0.2. Okay, so we've got 1.2 plus 0.2 plus 1.2, 0.2 plus 1.2 times 0.2. Okay, so let's see. That's 1.4 times 0.2 is 0.28, so 1.48. Okay, word of wisdom here, I'm going to go check myself, because if this is wrong, then everything else will be wrong. So that's the danger with Euler's method, is make sure you do this carefully, because if any of these are wrong, that error is just going to replicate itself. So all of the future computations depend on the previous one. All right, 1.48 is correct. So let me give you a chance now to go ahead and compute y sub 3. For y sub 3, I hope you got 1.856. Okay, so to get that, you want to do 1.48 plus zero point 0.4 plus this 1.48. So that's the right-hand side for this differential equation times 0.2. And assuming that I typed it into my calculator correctly, I got 1.856. Let me go ahead now and take this number and put it right into the next line. So 1.856 plus 0.6, that's the previous x value, plus 1.856 times 0.2. And again, with a calculator, I got 2.3472. And then this number goes right into the next line, 2.3472. Ugh, won't make a mistake, 'cause again, mistakes just pile up. So here we go. Plus the previous x value of 0.8 plus this one, 2.3472 times 0.2, getting us to what I claimed. This looks like it's times 2. I just want to be careful here the way I write this down. This is really times 0.2. And that leads us to 2.97664. I think that's an exact answer. I mean, for this computation, I don't think I rounded there. Regardless, we're saying that this is approximately y of 1, where y is the solution to the differential equation dy dx equals x plus y with an initial condition of 0 when x is 0, y is 1. Sorry, with an initial condition of y of 0 equals 1. That's what I'm trying to say. All right, so here we've got an approximation for the value of our solution when x equals 1. We've also generated, in addition to the initial condition, 1, 2, 3, 5 more points that we could use to try to create a picture of what the solution looks approximately like. Before we look at that picture, let me make a couple of remarks here. Again, I cannot stress enough to be careful with your computations because an error on the second line repeats itself on every other line. The other thing I want to mention is if you're just learning this and you've just worked through this example, keep in mind that every time we did x plus y in these parentheses, that's not the general algorithm. So be careful not to kind of write that down and circle it and remember it after this lesson. That's for this example, because this is the right-hand side to the differential equation that we're looking at. It's x plus y. If it had been x times y plus cosine of x, then this first computation would have been 0 times 1 plus cosine of 0. So what we did inside the parentheses here depends on the right-hand side of the differential equation. I just want to mention that in case you got in a rhythm of kind of writing down x coordinate, y coordinate, adding them together. That was particular to this example. Okay, let me step away in case I'm writing any of this down. And then what we're going to do to wrap up this lesson is look at a picture of what we've done. So this differential equation is not hard to solve by hand. I will give you the explicit solution with a plot because it's a nice function that we can easily graph in the xy plane, or at least graph with a computer. And then we will compare the graph of the real solution to kind of like a segmented looking estimate to the graph where we plot the total of 6 points that we have here and just connect those with straight lines. On paper, I was able to work out the true solution to dy dx equals x plus y with an initial condition of when x equals 0, y equals 1 by hand. And the solution is y equals 2 e to the x minus 1. For practice, let's verify that that is a solution. So dy dx, the left-hand side of our differential equation, if I just go ahead and differentiate this, I'm going to have 2 e to the x minus 1 minus 0. Okay, so that is dy dx, and I want to say that that can be thought of as x plus y. Given that I know what I'm looking for, what I can do is artificially bring in x minus x. I know to do that because, again, I know what I'm looking for. So I know I want to pick up an x somehow, and then plus 2e to the x minus 1. Now rearranging terms, this is going to be x plus, and then I'm going to put it into parentheses just to emphasize that it's y. This is 2e to the x minus 1. Now this is exactly what we're calling y. So this is x plus y. All right, so that is the solution to this differential equation. Now let me verify the initial condition as well. I should do that. So what is y of 0? It's 2e to the 0 minus 1. So that's 2 minus 1 is 1, which is exactly what we wanted to see. So this is the solution to this differential equation, or rather this initial value problem. I'm going to erase this just so that we have the full room to see the picture. So let me give you a minute to finish copying this down, and then we'll look at the graphs. Okay, now let's look at the graph of the true solution, y equals 2e to the x minus 1, and a picture of our estimate. So to this graph, let's add the function y equals 2e to the x minus 1. Notice it passes through the point x equals 0, y equals 1. The first thing we did was imagine the tangent line to this function through that point. We stepped with a step size of 0.2 to the right. That got us to our first new x coordinate of 0.2. Plugged it into the formula, and we got that y was 1.2. So that gives us this point on that tangent line, which we're saying should be relatively close to the true y value on the solution. Then we kind of start over. So from this point, we imagine a new tangent line. Step by 0.2 again. We got our next point, which happened to be x is 0.4, y was 1.48. New tangent line. Step to the right again by 0.2 to x is 0.6, y is 1.856. Step again on a new tangent line, and we got to x is 0.8, y was 2.3472. And then finally, to get to the right side of our domain from 0 to 1, we landed on a new tangent line with x equals 1, and our estimate of y of 1 was 2.97664. Okay, I've got the computation down here. All right. So let me remove all the extra stuff. Now we're just looking at the graph of the solution together with the points that we generated with the Euler's method algorithm, just connected by straight line segments. You'll notice that it gives us kind of a feel for how the function that solves this differential equation behaves. It's increasing, not as much though, okay, but it does give us an estimate if this is all we had to work with. Had we had a smaller step size, used delta x equals 0.1 instead of delta x equals 0.2, it'd probably be better. In fact, it would be better for this one. Okay, so we would have a nicer looking picture if we'd done, delta x is 0.05, could look even better. This is an underestimate. So notice we didn't increase as much as the real solution to this initial value problem. I would like for you to try to think of why. So let me give you a minute to ponder why we might anticipate, at least given the graph of the real solution, that our estimate was an underestimate. And for this, you just want to think of one of our major calculus concepts. So I'm looking for a qualitative aspect of this function that we use calculus terms to describe. Okay, so I'll step away and let you think about that for a minute, and then I will come back and give you a general principle for when Euler's method would give you an overestimate versus an underestimate. That our estimate was an underestimate is due to the concavity of the function y equals 2e to the x minus 1. So if you think of a concave up function, which like the one we're looking at, a concave up function sits above its tangent lines. So if I sketch some tangent lines left to right here, let's see if I can do that. That's actually pretty good. Okay, it's crossed a little bit more than I wanted it to, but all right. So if we draw some tangent lines, oh, okay, I'm actually really pleased with this. The function is above the tangent lines. So if you are at some point where a line is tangent to the function and the function is concave up, the function is going to increase from that point more than the line does. On the other hand, if we have a concave down function, then tangent lines, okay, see, this is what I was expecting was bad tangent lines. Okay, tangent lines are above. Let's just always remember that this picture went well, okay, and this one, not so well. That one's good. All right, okay. That's the idea though, is if our function is concave down, it's under its tangent lines. So if we had a concave down solution, we would be producing an overestimate. Now, if you don't have the solution, you can't take its second derivative and detect concavity, but you can analyze the original differential equation. We had dy dx was x plus y. What we could do is realize that by stepping to the right from x equals 0, our x coordinates are always going to be positive. And then our y coordinate started positive and it increased from there. So we were working in the first quadrant. The solution is going to be increasing because here the right-hand side is always positive. So we're looking at an increasing function that's staying in the first quadrant of the xy plane where x and y are both positive. If I take the second derivative, or if you prefer, you can write y prime prime. That's going to be differentiating both sides of this equation. So y prime prime is the derivative of the left-hand side. The right-hand side, if I differentiate that with respect to x, dx is just 1. dy dx is the right-hand side. So let me write 1 plus dy dx. But then that's 1 plus x plus y. So here, to replace this, I use the differential equation itself. If we're in the first quadrant where x and y are always positive, then the second derivative of a solution is positive as well. So we could have anticipated that our solution would be concave up and we would produce an underestimate.